try and build some particle accelerated demonstrations that you could use in a high school classroom. Here's some members of our group, and we had a mentor, and we had a second mentor because we had an absence. So what we're going to do in this talk is we're going to talk about. I'll give it a little. I'll start, and we're going to keep changing the mic, as you know. A little overview, description of linear accelerators and circular accelerators. We tried two different strategies. In each case, we'll talk about what demonstrations we developed, what the results were, and lessons learned in case you want to implement this in your own classroom. So the main idea of an accelerator is prepare a projectile, accelerate it, steer it, and then observe the results. And in our case, you'll see that we had to make some modifications from what you see in the actual accelerators. So we needed a voltage source. In this case, we used the Wimshurst machine. That works by you induce charge by rubbing surfaces with brushes. And there are two capacitors built into this thing, so it can actually store quite a bit of charge. One of the things about a Wimshurst machine, a typical Wimshurst machine, it's a random occurrence which side becomes positive and which side becomes negative. Unlike the Van de Graaff generator, which is designed based on which works based on the context with the belt. So if you have a Van de Graaff generator, it's probably an easier way to go than using this. This is what we use, though.
I'm sorry, I will sit. My dress has no place for a microphone. The basic principle of the accelerator is that a charge particle is exposed to an electric field which results in an electrical force.
Did you know?
To real accelerators, it works by manipulating the electric field. We change the polarity of the electrons with specified frequency. This will cause the charge particle that is moving from one electrode of the other electrode to get a kick in the desired direction. This is real acceleration, as we know, at the end of third week. But in our case, we use different techniques. In one case, we change the charge particle from plus to minus with specified frequency. In another experiment, we were moving location of the electric field, or we used opposite charge to conducting rings along the beam path. Thank you.
Maybe there's a cyclotron in here? Is there a cyclotron?
No.
All right, so with any accelerator, you need to do something to accelerate the particles and something to steer and focus the particles. What we've been learning about, of course, is mostly magnetic fields, in some cases electric fields to use the steering. In our high school version, we're using a combination of gravity and normal force to steer and focus our particles. I'm emphasizing this because we feel that's an important thing to emphasize, as you'll hear as we go forward.
And this is a linear accelerator. There is a tube. One of the wires from the machine. Okay. Which one? Yep. Oh. Sorry. one of the wires from the machine is connected to the end of tube. That end of the tube is then connected to aluminum foil, which makes electrical contact to the ball. The machine then transfers charge to the ball. The ball is repelled from one contact and attracted to other contact. Okay. And then we use the ground port from the machine, this one. It's to separate the voltage gap into two segments, like this. And this is the first attempt. Okay, are you ready? Oh, sorry.
Are you ready? Move the mouse.
Yeah.
Yes. Very good.
Do you want to see again? Okay.
Yes. Very good.
Yeah, I know it's a little bit short. So, and next we use the longer tube and attempt to the roll and the ball much farther.
I didn't even touch it. That's as far as I can get it. No? I got it all the way.
And we improved again.
You're never going to win.
And we made another design which used the ring of an aluminum can. As we move this ring, the ball is attracted and follow the ring. The electrical field is strongest near the ring. This is similar to the awake design.
I'm going to go 7.
And we asked an accelerator expert to comment on our design.
So, what was the question?
Can you have a traveling wave
Inside of this kind of cavity? Yes,
as
you
an
can.
accelerator?
For the acceleration, yes, you can.
And is it done in CERN anywhere?
This I don't know if CERN is done.
But you know someplace where it's done.
Yes.
Where is that?
I don't remember.
And lesson learned and step tips. Be careful of rim-shot zaps. We got a few victims. Yeah. And don't cross the wires. The plastic insulation is useless at this voltage. And be sure that foil is contacting the ball. Use a ping-pong ball with a conducting coating. Long wires dissipate charge. And plastic tube can develop a static charge. Then ball is always attracted to that spot. And the ground port on the Wimshurst machine allows you to have 3 different potentials for your demo.
Good.
Yeah. Thank you. I guess it's strong enough, no?
So inspiration for all, okay. The working principle of the cyclotron. The inspiration for this whole project was the cyclotron built here at CERN. Here it is. We saw it the second week, I think. You have a cavity. It's being vacuumed. And on the one side, it has a voltage. The other side is disconnected from it and have another voltage. And you have 2 huge magnets above and under. And finally, when the particles are accelerated fast enough, they will eject through this cavity and to a wall against it. And this will produce high-speed, high-energy particles that can be used for whatever scientific research it was used for. And this was actually the founding stone of all of CERN, as we remember, founded by the 12 founding nations in 1953. Some important discoveries were made by this machine, and this was basically the inspiration for all what we did. So here how it works. We have a cavity. One hemisphere of it is charged with positive voltage, the other one with negative. And we can alter currents from plus to minus on each side, which will create an oscillating voltage. Now, if we will put positive charges inside the cavity, in this case, we will use in the accelerator, the particles that were used are hydrogen nucleus, which are protons, positively charged. Now, if we will put protons in this situation, they will be repelled by the plus and attracted to the negative voltage. And if we alter the polarity of the voltage, we will get movement to the other direction. Now, the magnets are applying a magnetic field that comes from above or from the bottom, but is standing next to the cavity, and it will create, actually, if we will have a moving charge inside this cavity, it will create a linear motion. According to the Lorentz law, if we have a charge particle moving inside with velocity inside the magnetic field, it will bend over and move in a circular motion. And so probably it would look something like that. The protons are moving inside the cavity from side to side and getting speed. Now eventually the proton will reach the outer limit of this whole cavity, and at that stage it will find a hole, as we've seen before. When it will get there, it will fly out, and the quadrupoles will align the beam so it will go where we want it to go. This is the principle. Now, we couldn't actually build such magnetic fields, and we couldn't alter the voltage fast enough. So we basically altered the charge on the ball itself, which is impossible with protons, but is definitely possible with large balls like the one we use. Your turn.
Yeah, thank you.
Microphone. Oh, it didn't work. There you go. And there's another one.
Thank you, Hassan. Today, I want to show you in the basics of the create the cyclotron accelerator in your classroom. And the accelerator, you have the three parts for the important. The first part you have this is a generator, right? And the second you have an accelerator machine, and the most important part you have a particle. I want to show you in the picture is easy to understand. You can see this graph of pocket accelerator. You can make the accelerator use the ball and 3D printer. And the next is design and the detail of the height and distance of the ball. And this is a Wim Hertz generator, and this is a conducting bond. And I want to show you in step by step for how it works when you create the accelerator in your classroom. You not have magnet, right? And you can understand this is a picture. It's easy to understand. This is a circle. It's a ball, B-O-W-L. You understand? Yes, bro. I cannot speak English, bro. And this is a strip. It's a aluminum strip. It's a connected already. And this is a 4 strip. And this is a connect behind the ball. Yes, right. And when you connect the generator, the Wim Hof is a positive, right? And this is a positive all, right? And next, when you connect in this is a negative charge. Yes. When you spin the generator, is a create or build the high voltage, and between the positive and negative have an electric field. When you put the bond connecting bond to the positive first, is become to the positive charge. It look like the particle, and when you when it will move because the repel from the positive to negative. You can see the Assam demonstration. Yes.
I mean, microphone. Well, it's fine. You can continue.
Okay. This is a particle.
You.
Yes. Okay. And next, when the bond contact, when the bond move to the negative, is a touch or contact the negative and become to the negative charge, right? And next is a negative charge can move because this is a negative repel the negative and positive attack the negative. You understand? Yes. And and next, when it is the same continue when a circle, right? And this is a picture for the in the accelerator in the making. You have the ball and requirement equipment, and you making with a 3D printer for the ball or everything, and you take it. Yes. And I want to show you how it works from the cyclotron accelerator in your classroom. Yes. This is Asaf and Hassan. Spin the generator is produce the high voltage, and it works. Please trap your hand. Okay. And I want to send the microphone to Hassan. Say something to you. Yes. Thank you.
You got it.
Okay.
Thanks, Yuri. Okay, so this was it. In the next couple of slides, I'm going to tell you about our experience, our mistakes, our failures during this whole process. And it was really a great experience for us to explore different things and learn. But of course, we also did many mistakes. And so in next couple of slides, we're going to discuss those misconceptions or the blunders we made and how to improve them. So if you want to take this, and if you want to do this same demonstration in your class, so you will have more confidence. So let's continue. And how? This way. Okay, so failures and improvement. We made a lot of mistakes, but that's only means that we are trying. So from our mistakes and failures, we learned a couple of lessons, and in this slide, I want to share with you. The very first thing is that the material leakage. So in our first day of our this work group, we tried this glass bowl, and I think Alexandra brought this from her home, I guess. Thanks for this. We tried this one, and I mean, this looks very beautiful, at least from appearance, but unfortunately, we couldn't make it work. Which we were like very confused and frustrated why it's not working, because everything seems okay. But then we just realized that the glass, because the voltage we were providing through the Wim's machine or the voltage generator is quite huge, like 50,000 voltage approximately. So we just then realized that at the high voltage, the glass becomes conductor and it leaks the current. So it's a good idea not to use glass bowl, or maybe if you want just to show your students a bit of chemistry and things, you can just start from the glass bowl and then they would understand, okay, it's not working. So then we improved. We then used the plastic bowl, which is somewhere there, this one. And then you have already seen the demonstration of this one. So it worked. So this was the first thing. The second thing is that this was also very, very frustrating for us, that we were using the aluminum tape for the conducting wire instead of conducting for the conducting surfaces. But the thing is that this aluminum tape, they have a insulation at the bottom surface. So when we crossed these two wires, so it was not conducting the current. So to fix this one, you can either use another strip on top of that, or use a better wire. Like the copper is the copper one was fine because it has no insulating surface on the bottom. So that was something you should consider, and you should not waste time on this. Okay, and another thing which we have learned is the last demonstration Kanta showed you, the traveling wave. So this was also, and he also discussed, this is the idea of the Awake experiment, which is going to probably in 2020. But the idea was similar. So you can also introduce the very idea of what does traveling wave mean, and with this simple demonstration. Okay. Okay. So this was it. But then we were still thinking how to improve the design in this demonstration. So there were a couple of things which we considered. The first of all, to improve the the overall maybe the velocity or the trajectory of the ball. So we just thought of designing a ball ourselves, because of course it has some limitations, the curvature and things. We wanted to try different curvature, different geometry of the ball. So we just designed a couple of ball ourselves. So first of all, we designed a small, very tiny ball, just to see if the ball moves faster. But then it has other limitation because we didn't have the ball of the right size. So we designed a bit bigger one. For that, we used the online CAD software. It's onshape.com, and it's free of cost. It's a bit tricky in the beginning to learn, but after a while, once you get used to it, it's fun. There are some other alternatives available. Another idea, let me just show you. So this was the ball we were designing, and we also thought of designing a ball with having a kind of bump at the center. It's like a Higgs ball. So that would also give a push, or it would improve the motion or trajectory of the ball. Another thing which we just realized 2 days ago, but we didn't have time to print this ball, that ball, because of the time constraint, is that the curvature of this one is negative. But if you make a ball with a positive curvature, which means like the ball is going like this. So instead if the ball goes like this, do we have a chalk? So for example, if you make a ball something like this, then the ball could move and then faster and faster, and eventually it would leave the surface like a cyclotron does. So this was our idea, but we couldn't find time enough. But hopefully, once we are back to our
the voltage is not strong enough.
yeah. So, but then there are different options you can try. This was one of the idea. Okay, so we can of course improve this further. All right. So there were possible misconceptions to address. Of course, like when you are teaching this or doing this as a demonstration, hopefully you would do, then there are a couple of things which you want to discuss in the class. First of all is, I have listed a couple of things here. The charge on the particle. In an actual accelerator, the charge on the particle remains same. If it is proton, it's positive charge all the time. But in our case, the polarity of the ball changing. So whenever it crosses or touches the strip, it changes its polarity. So this is a difference. So you have to, of course, address this thing, because this is also very important to clarify the misconception. Otherwise, it won't serve the purpose, I guess. Size of the particle. So of course we were using this kind of giant like ping pong balls, but of course in the real accelerator you use proton, which is I think 200 trillion times smaller than this one. So of course you have to also consider many other things like the quantum mechanics if you go at that scale. And also this here we had only one particle, and in the real accelerator you have trillions of particles. So this also means that in order to keep them in one bunch, if you have trillions of particles and if you want them to stay in a bunch, so you also have to apply some extra physics or things. So it's not that simple, I guess. And also, this is also one of the most important things, is that in real accelerator we use magnetic force to bend, but here we use the mechanical force or normal forces. So this is also there's a difference. It's just a demonstration. And of course, the real accelerator use the protons or the particles. They move with the ultra high speed. That means you also have to account for the relativistic calculations. So make sure that you also introduce the differences to make it more productive and full of learning. Yes, here we have the CERN's motto or something. Like the main idea behind CERN is to accelerate science. Accelerating science, but the question is, how can we do that? Any idea? Of course there are many ways, but we just discovered that one of the best ways we can accelerate science by accelerating the particle. So if you just accelerate the particle, you can accelerate science. The idea is that you can clarify the understanding of the whole process. So with simple demonstration, you can really, really help students understand and learn and help them accelerating science. So I think this is just a humble suggestion for you to do. Okay, so this is kind of last slide. So we really want you to take the whole idea to your classroom and perform this, and to accelerate science and everything. So there are a couple of things you have to consider if you want to take this to your classroom. The very first thing is that, as I discussed this is a very interesting demonstration. So we would sincerely recommend you to please try this in your classroom. Next thing is that while you do that, make sure that you are also explaining the differences between the real one and this one. That's, I think, the key factor in learning the idea behind all these things. Sorry. Okay, and also once you plan this demo in your classroom, make sure that you have at least 2 hours of preparation, because it took us like 2 days. So I think 2 hours for you is enough, because you have already seen the problems and failures, so you can quickly improve. But at least it would still take at least 2 hours to build and test this thing. And next thing is, of course, you already know that you have to be very careful and very well organized, because the voltage source which we use generates a huge amount of voltage difference, which goes to 60,000, 70,000 volts.
Yeah, when the machine is actually working, only the teacher can touch it.
So make sure that you are the one who are. I mean, of course, you make sure that you control the environment there. But of course, you already know this thing, I guess. But don't worry, this is not lethal. I mean, this is high voltage, but the current is not that much, so it's not a big deal. But still, make sure that everything is under control. Okay, this was it, and I want to thank you on behalf of all my colleagues. Thanks.
Thank you so much for this presentation, a perfect start in the day. I really enjoyed the videos. We are running a little bit late, but we enjoyed it, so 10 minutes more, why not? But we have to speed up a little bit. So, any questions or comments or remarks or selfie requests? Maybe don't play with the microphone. Yeah, we have one intrinsic problem. Daniel, you are in the group. So who is going to ask questions here, guys? Daniel, you want to ask?
I can say one thing. You can play with the toy later when it's sitting outside and it's working.
Oh, very nice. Now everyone in the video conference will be super sad because they will think, oh, there's something outside my door, and it's not. Any other questions? Thank you for laughing. Okay, well, in this case, I would love to thank the group one more time for this excellent presentation, so please help me and clap for them. I also